What lies beneath? Evidence of life under the Antarctic ice. That extreme life forms might exist in the cold and dark lakes hidden kilometers beneath the Antarctic ice sheet has fascinated scientists for decades. Understanding how life can exist in the most extreme conditions on Earth can help us to understand how and where life might exist elsewhere in the solar system. But taking direct samples from these lakes deep in the Antarctic interior poses major technological difficulties, not least of which is drilling through more than 3 kilometers of ice to reach them. Instead along with other scientists at the British Antarctic Survey, University of Durham and University of Ghent examined the margins of the retreating ice sheet, looking for subglacial lakes becoming exposed for the first time since they were covered by ice more than 100,000 years ago. We discovered one, Hodgson Lake, when we noticed an unusually flat area a few km from where we were working on the George VI ice shelf. The following year, we returned, drilled for samples of its water column and sediments, and climbed the nearby mountains to glean from examining the rocks how thick the ice had been over the lake. The ice had been more than 500 meters thick and only started to thin in the last few thousand years. The lake is now easily accessible as a result of natural ice thinning and accelerated melting due to the enhanced global warming at the poles. Drilling down into the sediments, we were able to sample the layers deposited when the lake was buried and, for the first time, could look for evidence of the life that might survive in this under-ice environment. We could date the sediment by archaeomagnetic dating, which examines past changes in the Earth's magnetic field. Our first efforts to find life were largely unsuccessful. Nothing could be seen under microscopes and the chemical signatures of life were difficult to separate from normal chemical reactions between rocks and water. So my colleagues David Pearce, Charlie Cockle, Gavin Burns, and Michael Thorne, specialists with the latest molecular methods, analyzed fragments of DNA in the sediments. These are particularly well preserved in the cold and dark and can be compared with global DNA databases to identify the organisms from which they were derived. We found no multicellular organisms, but the fossil DNA showed many different types of bacteria live there, including a range of extremophiles, species adapted to the most extreme environments. One DNA sequence was related to the most ancient archaebacteria known on Earth, and as 23% of the DNA has not been previously described, many of the species are likely to be new to science. There is evidence of life in almost every environment, with bacteria present in rocks deep in the Earth's crust, in sulfurous springs, methane seeps and the hydrothermal vents at the bottom of the ocean. So while we anticipated finding some species adapted to the cold, dark, high-pressure environment under the ice, we found a much larger variety than we expected. DNA sequences that encompassed the full range of bacteria encountered in marine or terrestrial ecosystems, including a number of groups not normally associated with extreme environments. We also found bacteria that live in environments with and without oxygen and others which require sulfur or methane to survive. This implies that a diverse range of biological activities occurred in the lake when it was under the ice. These findings have implications for understanding the habitability of extraterrestrial environments. That the deep cold habitats of subglacial lakes support life suggests that similar extraterrestrial environments, such as on Mars or the Jovian moon, Europa, might be promising candidates for exploration, though whether they are inhabited or not remains unknown. The difficulties of accessing much deeper subglacial lakes remain, and teams from the UK, US and Russia are still working on overcoming the technological challenges. Our British team at Lake Ellsworth ran into technical difficulties attempting to drill through thick ice. The American team managed to collect samples from Lake Williams at the edge of the Ross Ice Shelf. This 2 meters deep lake is under 800 meters of ice, similar to the ice cover over Hodgson Lake during the last glacial period. The results from Lake Whillans will add a further valuable dimension to understanding life in these systems. The Russians have reached Lake Vostok and taken samples of ice immediately above the lake that has also been analyzed for signs of life. The sediments in Hodgson Lake have given us a first look at life in the sediments of Antarctic subglacial lakes, but of course the deepest and most remote lakes still remain largely unexplored. What we have learnt from Hodgson Lake will help inform our sampling of these most remote habitats. The technology will be more refined by then, the cleanliness protocols more effective and better validated, and the molecular biology methods much more sophisticated.